Okay. Hello, everyone. Today I'm going to talk about Vulkan compute and compute shader. So let's start with some background information about graphics. GPUs used to be just triangle render machines with fixed function pipeline. That means they can only do some specific jobs without much flexibility. But over time, GPUs became more and more complicated. They became more and more like CPU due to the need of executing shaders. Before working as rendering machines, modern GPUs are parallel compute machines first. So at the beginning of 21st century, engineers find GPUs are a perfect fit for scientific computing, such as solving embodied problem. They have since been developed in this direction. Eventually, graphics APIs added compute shaders, which allow running arbitrary computations on the GPU. Vulkan is designed to be both a graphics and compute API. So we can consider Vulkan Compute as a subset of Vulkan APIs. It shares many components with Vulkan Graphics API, but Vulkan Compute is much more simple. So a typical program using Vulkan Compute only has 4 stages. The first stage is hardware setup. So in this stage, we can query the hardware platform. We can choose a suitable physical device. We create the device and get the compute queue index. In the next stage, resource setup, we create buffers and update those buffers with input data if necessary. In the third stage, pipeline setup, we create a compute shader module and spatialization constants. We can also connect buffers to the pipeline here. In the last stage, command execution, we create command buffers by recording commands, and we submit command buffers onto the compute queue to start the computing. And this figure illustrates the structure of a program using Vulkan Compute from the perspective of Vulkan objects. Different colors represents different stages, and the blue represents the first stage, which is hardware setup, and the green represents resource setup, and the brown represents pipeline setup, and the and the right represents the final stage, command creation or command execution. So one problem is, how do we transfer data between GPU and CPU? So we use buffers and constants. For Vulkan Compute, we have 4 options. The first one is using spatialization constants. They are embedded into the pipeline, but cannot be changed after the creation of pipeline. They are not flexible, but it has one important feature, that they can sneak into shader and manipulate some constant at runtime. We will use spatialization constants in our demo, and I will show you later. The second option is using push constants. Push constants have limited size, usually no more than 256 bytes. It's really small, but it provides data to shaders in very simple and performant way. It do not push constants do not use any video memory. So they use some mechanisms to transfer the data directly into the shader. They are embedded into the command buffers, so you have to reconfigure your push constants each time you reconstruct your command buffer. So that could be a drawback. So the third option is using uniform buffers. Uniform buffers are also small, but up to a few kilobytes. It is bigger than the push constants. And uniform buffers are fast, but they are read-only, so they are perfect for shader parameters. The fourth option is using storage buffers. Storage buffers can be much bigger, although they still have device-specific limit. For example, on my graphics card, the storage buffer cannot be bigger than 2 gigabytes. Storage buffers are slightly slower than uniform buffers, but they are writable, which means we can fetch data from GPU side to CPU side via storage buffers. Then I will briefly talk about compute shader. A compute shader is a shader stage that is used entirely for computing arbitrary information. Unlike the graphics pipeline, which has several stages such as vertex shader, tessellation, fragment shader, the compute pipeline only have one stage, which is compute shader. So compute shaders do not have any pre-stage or post-stage. So compute shaders have no user-defined inputs, and there are no outputs. GPUs are parallel compute machines, so we can run compute shader on multiple compute units simultaneously, but invocations of compute shader are split by workgroup. So why we need this concept workgroup? This is because of the architecture of GPU, as we can see in the following figure. So the compute unit, which are the green blocks, are clustered into a small workgroup first. And each workgroup has individual cache and control unit. And after that, those groups are clustered together as GPU. So it's easy to understand why invocations within the same workgroup can effectively communicate, since they have shared cache and control unit. And on the contrary, the communication between different workgroups would be inefficient. And the space of workgroups is three-dimensional. Although compute shaders do not have any user-defined input or output, they do have built-in input variables. We take GLSL as example, but it would be similar for other shader languages. So the first variable is the in keyword means this is an input variable, and the uVec3 means this is a unsigned int vector with three-dimensional, and the GL non-workgroup represents the number of workgroups along three dimensions, X, Y, and Z. And next one is GL workgroup ID. It represents the workgroup ID for current shader invocation. The local invocation ID represents the current invocation ID within the current workgroup. And the global invocation ID is the invocation ID among all invocations. And the last one is local invocation index. It is just the 1D version of global invocation ID. We also have a constant called GL workgroup size. It represents the size of the workgroup. Note that it's users' responsibility to set up two of these variable or constant. The first one is the number of workgroups. We need to set up this value on the CPU side when we dispatch our compute works. And I will show you code later in our demo. And we also need to set up the workgroup size. And in most cases, we just hard code the size of workgroup in the compute shader, but with the spatialization constants, we are able to configure this value in at the runtime. So next, I will show you the demo I built for this presentation. So this demo contains two programs. The first program, Mandelbrot, can generate Mandelbrot set image in PNG format with given width and height. And Mandelbrot supports both GPU computing and CPU computing using Vulkan and OpenMP respectively. And the second program, Benchmark, simply outputs the time spent for generating a Mandelbrot set image via GPU and CPU. This demo is available at the following URL. It's public repository, so you are free to download code and run the code on your own machines to see the results. So next, let's move to the source code of our demo. So the first software I want to show you is the main function of program Mandelbrot. So this function have 3 parameters from command line. The first 2 are the width and height of our image, of our target image. And the third option, the first 2 options are required, and the third option is optional. It determines we use the Vulkan Mandelbrot generator or the OpenMP Mandelbrot generator. And after fetch the raw image data from the generator, we use a lightweight library called LoadPaint to encode the raw data into PNG format, and we then simply output the data into the standard output. So next, I will go into the class Vulkan Mandelbrot generator. Sorry, we need to go to the declaration first. So that's here. Okay. So the class Vulkan Mandelbrot generator has only has one constructor, and it has 2 parameters, which are the width and height of the image we are going to render, and it only has one public member function, which simply returns the raw data of the Mandelbrot image we rendered. So in the generate function, we just follow the stages I described previously. So the first stage, hardware setup, we create instance, and if we enter debug mode, we also set up some debug messengers to output the debug messages to the standard arrow output. We also find physical device, create device, and then at the second stage we create buffers, and then it's the third stage. And this code are almost self-documenting, so it is not hard to read at this stage in this function. And for a fourth stage, command execution, and finally we after submitting the command buffer, we fetch the rendered image from VRAM to RAM. And finally, don't forget to clean up all the resources you allocated, you created, and in the end, we return the raw image. Next, I will show you the compute shader source file. So we use so we use GLSL here, and we use version 450. And the first thing we do is to set the local workgroup size via specialization constants. So you can see we simply specify the ID here. So the ID for local size X is 0 and ID for local size Y is 1. Otherwise, if we do not use specialization constants, we have to hard code the workgroup size in the compute shader, just like the following code. We just simply assign 32 to the local size S and assign the 32 to local size Y, for example. This is not good, since if we want to change the workgroup size, if we want to, for example, we want to optimize our code to find the best size, we have to change the value, recompile the shader over and over again. So we choose to use specialization constants, so we can just configure these values at runtime. The next is storage buffer. So we use storage buffer to store the image buffer, since we want to fetch the image data from GPU to CPU, so we have to use the storage buffer. And for some compute shader parameters, such as the size of the image, we use uniform buffer, and it is just here. And in the main function, we first to terminate some invocations, since in order to feed the work group into work groups, some and necessary invocations may launch. So if the global invocation ID is greater than the size of the image, we simply return this function. We simply return the main function. So the code in line 27 to 41 is just the code for computing Mandelbrot set. And we then use a cosine palette to determine the color of pixels. And finally, we store the color data into the storage buffer with appropriate index. We use global invocation ID plus the weights, and then added the global invocation ID X. And basically that's the compute shader. So we will go back to the Vulkan Mandelbrot generator. So we will look at some functions. The first one we want to look at is create buffers. In this function, we first create storage buffer and bind storage buffer memory to this to storage buffer, and same, we create uniform buffer and uniform buffer memory. And since we want to transfer the size of the image to the compute shader via uniform buffer, we can do the transfer here. Since the uniform buffer memory is host visible, which means the memory so memory in the GPU are visible to CPU, so we can simply map the memory into a pointer, and then using memory copy function to directly copy the data into the VRAM. And the uniform buffer memory is also host coherent, which means we do not need to flush the data manually. So we just copy the data and then map the memory and done. So the next function I want to show you is create compute pipeline. So in this function, we first read the source file of compute spare V file, and then we construct the shader module create info, and we create the shader module use the create info, and that's a typical way to create objects in Vulkan. And what I want to emphasize here is the specialization constant. So we use the specialization map entry to tell the Vulkan the layout of our specialization data. So we use a strut called workgroup size to specify the workgroup size for our compute shader. And you can see we set the constant ID 0 and 1 here, corresponding to the ID in the compute shader. Here, we also assign 0 and 1 here. And then we just do some other jobs. We just tell the Vulkan where the size of our workgroup, the size of the workgroup size object, and we pass the pointer of our workgroup size instance to the specialization info, and then we can pass the pointer of the specialization info to the pipeline shader stage create info. So the pipeline shader, so the pipeline will know how to use the specialization constants. And finally, we just create the pipeline use several create infos and down. And next, I will show you how to use the program. So these programs are pre-compiled, so I will just show you the result. So we just use the Mandelbrot, and we want to generate a 16K image, pretty big. So the size of a 16K image will be this, and we just redirect the output to GPU ping and wait for a few seconds. It's a pretty big image, so it takes some time. Okay, it's done. So let's see the result. Okay, let's open the image, and we can see the Mandelbrot set image here. So it's a 16K image, and we can zoom in, and zoom in. Oh, it's still pretty clear here. And also we can also use OpenMP to generate Mandelbrot set image via CPU. So we just add another option here, 1, and redirect output to CPU PNG. So this may take 30 seconds since the CPU using CPU is much it's pretty quick. So maybe the bottleneck is not the rendering itself, it's the encoding part. So we got the same result. Okay, so the next program is benchmark, which simply using both generator to render same image and output the duration. So just in the benchmark, we do not encode the raw image data. We just fetch the rendered image raw image data and output the duration. So we can see the Vulkan is much faster than using OpenMP. And another thing I want to say here is I'm pretty sure when using OpenMP, the CPU usage will close to 100%, but the GPU usage when using Vulkan could be under 10%, since we only render one image here, so we do not utilize our GPU effectively. So if we, for example, if we want to render thousands of images simultaneously, and we will see the real power of using Vulkan compute. And this basically that's all of my presentation. So thanks. Do we have any questions?
I can ask some questions.
Okay.
So one thing I was wondering, in terms of the benchmarking that you were doing, I'm curious if you had a chance to look into like where the time is being consumed. Like I'm wondering how much of the time is being spent like transferring the computed image from the GPU back to the CPU. Like, well, I guess the image is quite large, so probably a lot of the time is for the computation. But I'm wondering if it's how significant the copying is, because as I understand it, this is often the bottleneck when you're using GPUs for computation is when you have to be transferring data back and forth between the GPU and the CPU.
Yes.
So I'm wondering, because you're generating a fairly large image, I guess. I'm wondering like how much time is spent actually copying the result, like from the GPU's memory to the CPU's memory. Is it relatively insignificant compared to the other, like the computation time?
Okay, I will do it right now, so it won't take too much time. So
Oh, sure.
we will see the result.
I guess because the image is so large, probably the computation time will dominate even over the memory copy. But I'm just curious if it's
Interesting.
negligible or whether it's even an issue at all.
Okay, so we will just
I assume that those would probably be the two most significant costs, the computation and probably the transfer of the data at the end. I'm assuming probably that the setup is fairly small, like the initialization, but maybe that's wrong. I don't know.
So we can just, yes, I'll put the operation. So Let's build the benchmark. So this is a 4K image, so we use 16K image. Well, is 1,167 milliseconds. Well, it's price made, so it
So
really
that's about
consumes.
half, I guess. Am I reading the numbers right? It's about half the time then?
It's 1,167, so 1137 milliseconds.
Yeah, but is the Vulkan number the total time for the Vulkans, and then the 1173 is like the amount of time of the
entire time for Vulkan is. Can you see my screen?
Yeah.
Here.
So does that mean that fetching is about half the time then, or
yes,
like slightly?
Yeah,
okay.
More than half the time. So.
Okay, it was actually more than what I thought. I was wondering how significant it might be.
So if we do not want to fetch the data from GPU to CPU, if we just display this image to on the screen, so it will be much faster.
Yeah. And maybe one other question I have, you're doing like a 15360 by 8640 image. I'm wondering like how large can you make it? Is there like a practical upper limit that's imposed based on whatever particular GPU hardware you're using? Or if you make it really large, will it do some kind of, I don't know, like how fancy does the GPU handle like running out of memory? Like basically when you run out of memory, it basically can't handle that? Or does it do something more fancy to try to I don't know.
Yes, it has a.
Like I guess phrasing it another way, like how large can you make the image for the particular GPU hardware that you have before things break and it doesn't work anymore? Because I assume at some point you'll run out of whatever resources are needed for the buffers.
Yes. If we only use one storage buffer, so each storage buffer have a device specific limit. So on my graphics card, it is 2 GB. So if we want to, for example, if we want to Mandelbrot a super big image, and to it will throw exception that we cannot create. Oh, sorry. We need to reduce the size. Maybe okay. It's too small. Stop.
I guess the main buffer that you're using in your program is the one that's holding the image that you're computing. So if you have 2 GB for your like graphics card, then basically you can accommodate an image that's approximately 2 GB in size. Is that accurate?
Yeah.
Okay.
Approximately 2
So
GB.
it's a pretty big image, I guess.
Yeah. So it can handle a 16K image, which could be the 16 times to the regular 4K image.
Yeah, that's pretty big. At first, I thought maybe it was misunderstanding your command line options, but like 15,000 by 8,000 is a pretty big, a pretty high resolution image.
Yeah. We can just add a 0 here, and it must exceed the size limit of storage buffer, but we're using the release version. Yeah. I don't know, but I'm pretty sure so if we maybe we should using the debug version to see the uh, debug information from validation layers. So just view the debug version. And so just Mandelbrot, just copy it. It shouldn't be that long to output error messages. So I don't know. Maybe I will debug later.
Yeah, not a big problem. I noticed that you're using a bunch of functions in the VK namespace. Is that essentially the Vulkan library that you're using, like the C++ language binding for the library you're using, or is VK some of your own code that
Yes,
you've written?
I'm using the Vulkan HPP, which is the C++ binding for Vulkan C APIs.
Okay, so all the stuff in the VK namespace are coming from that header file then.
Yes, yes.
Okay, I just was wondering, yeah. And I'm curious, I guess you could also implement this using OpenCL, like you could,
OpenMP.
oh, sorry, yeah. Oh,
I'm
wait a
using
minute. The OpenGL implement, or sorry, you're comparing, you had Vulkan and then you were competing with the CPU. I was wondering, like,
Yes.
I was wondering if you, what would you expect if you used OpenCL? Because I guess OpenCL is not the same as Vulkan with the um, compute shader, is it called? Sorry, I might have the terminology wrong.
I'm still learning OpenCL, so.
Right.
Right,
Okay,
so,
but it's a different thing, right? So like Vulkan with
yeah.
the compute shader is a different thing. Like OpenCL is like a completely different library, as I understand it. So I guess you could also implement things that way as well and compare. It'd be interesting to see, you know, which one is faster, or maybe they're about the same, or whatever. I don't know any. I've not done programming with either one of them though, so I don't really have any good feeling. You know more about this than I do.
Yeah.
Do I have any other questions? I was a little bit, this is just my stupidity. Like I haven't done any programming with Vulkan, and the little bit of programming that I've done with shaders and GLSL was quite a long time ago. But I'm wondering, I'm a little bit fuzzy about what the global invocation ID is. Is this like an instance, sort of like a thread instance or something like this that's running on the GPU effectively? Like, or is
Yes.
it?
Yes. The invocation ID is just uh,
Is it like each thread of execution on the GPU has its own?
yeah, each execution of compute shaders.
Mm-hmm.
One invocation, it is just the invocation of the compute shader. So the invocation ID is just the just ID of the. I don't know how to explain that, but
So it would distinguish if you have like the shader running, maybe you're computing multiple Mandelbrot images at the same time or something like that, but it's identifying the particular invocation of the shader, like the shader instance.
in this case, I prefer to say that the invocations are represent the pixels, since we in the compute shader we render we render our image pixel by pixel. So
Mm-hmm.
we have one invocation for each pixel, and so the uh, the global invocation ID would just be the coordinate of the pixel in the image.
Mm-hmm.
So and. And oh, I forgot to say that we configured the work group, the number of work group here in the function. Sorry, in the function submit command buffer. So the create command buffer. So when recording the command buffers, we tell Vulkan the size of the non-work group, and it is calculated by divide the weight of the image by the work group size, which is 4 in this case. With 4 or 8, it is hard. The size is hard coded, and so we dispatch we tell the Vulkan the non-work group X and non-work group Y here, and we also tell the computer shader the work group size of the work group size used in computer shader. So if we multiply the number of work group and the size of the work group, we get the total number of invocation of computer shaders, since we rendered our image pixel by pixel. So one computer shader for one invocation of one pixel, one invocation for one pixel. So
okay, I shouldn't monopolize the question asking. So Young Soon, if you have any questions, please feel free to jump in. And some of the other remaining questions I have are maybe kind of stupid because again, like I don't know Vulkan, so probably some of the questions are better just left outside of the recording itself.
Yeah, I just want to make sure that we have to compile share the first file.
yes, we have to pre-compile our shader source file. So you can see the source file here is shader dot compute, and we use command here. We use GLSL to compile the GLSL source files to spare V files, the intermediate format used by Vulkan. And then in the creation of compute pipeline, we read the spare V file.
Were there any other questions, Young Soon?
No.
Okay, maybe just the last comment I'll make. I thought the presentation was quite well done. I think you probably spent a fair amount of time preparing for it, so good work.
Thank you. Thank you, guys.